Very good. So it's a pleasure to have Sam van Leuven, who is a postdoc at Wits University at the Mandelstam Institute, I would imagine. And Sam will be talking to us about the modularity of the n equals 4 superconformal index and ADS5 black holes. Welcome, Sam. Take it away.
Okay. Thanks, Jeff, for giving me the opportunity to talk. And no, I also prefer to have the seminar informal, so please interrupt for any questions. So the title, Jeff already said the title of the talk. This is mostly based on a paper that appeared last April, the 2104 paper. But there was some we did some preliminary work at the end of last year. So this is in collaboration with two profs at Wits, Kevin Goldstein and Vishnu Jejela, and then also colleagues, an ex-postdoc here at Wits, Yang Lei, who's now in Beijing, and Wei Li, who spent her time partly in Beijing and partly in Zurich. Okay, so let's get started. So I'll give a rather extensive introduction. I'll spend, I think, more or less half of the talk on the introduction, just to set the stage, get everyone on the same page, and update you on some really recent developments in this story. Okay, so let me start. First of all, we all know that semi-classical gravity predicts that black holes behave as thermodynamic objects. So in particular, they have a temperature, the Hawking temperature, and an entropy, the Bekenstein-Hawking entropy. And the Bekenstein-Hawking entropy is given by the area of the horizon of the black hole over 4G Newton. So a central question in our field is, what is the nature of the microstates counted by this entropy? Or in other words, what is the statistical interpretation of this entropy? And an answer to this question requires a non-perturbative theory of quantum gravity, which at present we don't have. But perhaps this is us preaching again to the choir, but we all think, I guess, that string theory is a promising. Sorry, there's background noise.
Sorry.
Okay, that's fine. Yeah, so string theory is a promising candidate, and indeed, in the context of string theory, there was an important breakthrough around this question by Strominger and Vafa, who studied 5D supersymmetric asymptotically flat black holes. So let me just briefly say what they did, summarize what they did. So they had a microscopic realization of this class of black holes as a so-called D1, D5P system. So, what I illustrated here in the left figure is the intersection of D1 and D5 branes. So they intersect spatially over a one-dimensional line, and you can imagine that time goes up here. And this system at very small values of the string coupling is some effective world volume theory, a CFT2, that describes sort of the low energy excitations of the open strings here. All right, so that's at weak string coupling. But now you can imagine to turn on the string coupling. And if you have sufficiently many D branes, this will be these branes will backreact on the geometry, and they will create some black string. So they curve the geometry, and they ultimately collapse into this black string geometry. And then the idea is that this system sits in 6 dimensions. And then when you reduce a dimension along the length of the string, you get these 5D black holes. So Now you can compute for a fixed number of d-brane charges and momentum. You can quite easily compute the number of microstates of this d1, d5p system. So that can be done, for example, by using the Cardy formula in CFT2. And that it turns out that precisely gives the black hole entropy. So that's perhaps a little bit surprising, but the key point here is that because of supersymmetry, this number of microstates is protected. So it's not renormalized as you turn on the string coupling. And that's why sort of this d-brane system that is only valid at weak coupling still gives the correct result for the entropy. All right, so this was a very big progress. And then after this paper, many generalizations appeared. So black holes were studied in different dimensions. The supersymmetry condition was a bit relaxed. So you can study near BPS or nearly supersymmetric black holes. You can study extremal black holes that do not necessarily preserve supersymmetry and near extremal black holes. But it turns out that always in all these generalizations, it is actually always this Cardy formula and an effective CFT2 that allows you to really compute the number of microstates, at least as far as I'm aware. Sorry, I was being a bit quick. So what I actually also want to say here is that this breakthrough was just before the ADS-CFT correspondence was discovered. So, and the ADS-CFT correspondence is actually very similar in spirit to this idea of having a d-brane system and letting them back react on the geometry and getting a gravitational solution. And so, in fact, this d1, d5 system gives rise to one of the prominent examples of the ADS-CFT correspondence. And the statement is that in the near horizon geometry of this black string, which has an ADS-free factor, that the full type 2b string theory in this near horizon geometry is equivalent to the low energy dynamics of the open strings on the d1, d5 intersection, which is described by some two-dimensional CFT. So the microstates of the black hole are then explicitly realized in the CFT2. And in the context of this ADS-CFT, the 5D black hole reduces to a BTZ black hole. And then it is indeed also well known that the Cardy formula in CFT2 computes the entropy of a BTZ black hole. So as I said, all these generalizations, they somehow always make use of ADS-free CFT2 and the Cardy formula. So it's natural to ask if we can also if we can compute the entropy of black holes without making use of this. You know, this is somehow rather specific to specific types of black holes, and we want to know, yeah, are there other methods to do this, and can we learn something from that? And a natural setup to address that question is to just study higher dimensional ADS-CFT, where you don't have a CFT2 necessarily, and thus not directly a Cardy formula. So in this talk, we'll focus on the prototype ADS5 CFT4 correspondence, which among other things states that type 2b supergravity on ADS5 causes 5 is equivalent to the n equal to 4 SUN super Young-Mills theory at large n and strong coupling. And yeah, because we want to analyze black holes in this supergravity theory from the CFT perspective, from the, you could say perhaps microscopic perspective, we have to deal with strong coupling. And the way we deal with strong coupling is that we going to restrict to supersymmetric states, supersymmetric black holes, because then, as in the Strometer-Vava case, you have these non-renormalization theorems, and you can compute things at weak coupling and then extrapolate the strong coupling. All right. So any questions about that general setup?
Yeah, I have a question. First, I should
Yes.
apologize because my kids are being loud and you might hear some stuff in the background.
That's no worries. No worries.
And so you know, Strominger-Waffer is really what got me into string theory, believe it or not. It says, you know, I had started studying black holes in the context of, I guess, what would be loop quantum gravity when I started my PhD. It wasn't really, it was kind of the dual of loop quantum gravity. But I then, you know, from there, I kind of got into, I discovered the analog loop quantum gravity results, counting of microstates. This is Smolin and Rovelli. Found that to be rather impenetrable result. Looked around and discovered Strominger-Waffer. And then, you know, Strominger-Waffer turns out to be this beautiful realization of how to count black hole microstates. And that's kind of, you know, what got me into string theory. And it's been a long rabbit hole since then. But I wanted to ask, you know, what is the state of the art now, today, in terms of counting black hole microstates for non-supersymmetric black holes?
For non-supersymmetric. That's yeah, and by that do you mean you know, far from BPS, or I guess you mean that?
I do. I mean far from BPS. I mean, you know, where we don't have the control that supersymmetry gives us to dial up the coupling, for example. You know, so. I know Susskind and collaborators back in the early 2000s, I guess, had some work, you know, that kind of was related to the BFSS model, matrix model, and you could take, you know, so effectively you were computing it for four-dimensional boosted Schwarzschild black holes, but I lost track of what people were doing, because then fuzzballs were invented / discovered, and the community kind of moved towards these exact solutions. And then, you know, some fraction of the community, which I guess I paid more attention to, is moved into low dimensional black holes, and not just BTZ, but also, you know, JT gravity and that. And I've been paying more attention to that. But what was the state of the art? What is known in terms of the black hole microstates for four-dimensional non-supersymmetric, let's say far from BTS?
It's a fair question, and I can't be sure of the answer, but I believe that there's not that much progress on that, to be honest. But so yeah, so part of what I'm going to talk about today is still supersymmetric, but it really somehow uses different methods than the Cardy formula in 2D CFT. So it is in that sense, and you know, it's about really ADS5 there are ADS5 black holes and similar developments in ADS4. But for, you know, proper Schwarzschild, for the proper Schwarzschild solution, I'm not really aware of any progress. Of course, you have the Kerr CFT story, but then, you know, supersymmetry is somehow traded for extremality. Yeah, but so I might be wrong, because but I don't believe that there is significant progress on the fully non-extremal case. Of course, for the BTZ, we do know. For non-extremal, non-supersymmetric BTZ, we know we can do it, but yeah, that's again that Cardy formula. Beyond that, yeah, I'm not aware of anything more.
Okay, thanks.
Yeah. All right. So then I'll continue with the black holes that we're interested in. So just a brief description. So this type 2b supergravity can be reduced on the S5, and you get some 5D n equal to 1 U1 cubic gauged supergravity. So here the U1 cubic gauge group corresponds to these isometries of the S5. And it turns out that this theory contains asymptotically ADS5 black holes that preserve a supercharge, complex supercharge. So those are the main characters here that we want to study. These, by the way, these have they have finite area, finite entropy. So these black holes, they carry angular momenta. There are two independent angular momenta in ADS5. Corresponding to the angular directions, which form an S3. And then these can also have electric charges with respect to these U1s. And they satisfy, because they preserve a supercharge, there's an associated BPS condition on their mass. So their mass is determined in terms of the charges as follows. And this L here is the ADS radius. So you can just, these solutions are explicitly known, and you can compute the area element on the horizon, and the entropy turns out to be given by a relatively simple function. So it's, as is common for supersymmetric or extremal black holes, it's purely given in terms of the charges. And this is what it is. And this is what we ultimately want to derive from the field theory, from the CFT4. Now, you can also note that for large enough charges, this entropy will be larger than the ADS area in Planck units. And through the ADS CFT correspondence, this corresponds to n squared, where n is the rank of the gauge group of the n = 4 theory. So this is a reflection of that famous idea that black holes in ADS5 correspond to the deconfined phase in the dual gauge theory. All right, so onto the CFT dual, which is the main character in this story. So the dual states to these black holes should be 1/16 BPS states in the n = 4 SUN Young-Mills theory. And there's an interesting function or partition function that counts these states with signs. So let me explain that. So it's called the Superconformal Index. So let me go through it in a bit of detail. So here there's a trace. The trace is taken over the Hilbert space of this theory quantized on S3, which because it's a CFT, you can construct this Hilbert space easily by acting with local operators in flat space.
Sorry, Sam, can I just interrupt for a second?
Yes.
A lot of the, let me just double check to make sure I'm saying the right thing. Okay, so a lot of the audience here are students who are not necessarily familiar with all of the jargon. Could you maybe expand on what a BPS state is?
Yeah, of course.
And you know, the various fractions. Thanks.
Yes. So I think, yeah, I'm sorry if this is already a bit technical to the students. So a BPS states is so do people do the students know about this supersymmetry algebra? And
I would imagine that some do, but not all.
Okay, well, okay. Let me try to set it up briefly. So actually, I will come there, but let me say it now also. So supersymmetry is a symmetry that relates bosons and fermions. So a supersymmetric theory has a spectrum, and in that spectrum, a general state in that spectrum has say there's some bosonic state in the spectrum, then there will be a corresponding fermionic state. And just like you can time translate a state using the Hamiltonian or something like that, you can also act with a Q operator, which a Q operator on a state, which represents a so-called supercharge, and this maps the bosonic state to a fermionic state. So that happened. Generically, these states occur in pairs in a supersymmetric theory. And then this n here, this n equal to 4, indicates actually that these pairs of states can actually be bigger. So this n equal to 4 means that you can, in some sense, have really 16 paired up states that sit in that are mapped between each other with a number of these Q operators. So n indicates how many distinct Q operators there are. And now, okay, so that happens for the generic states, but then there are some special states that do not have a partner. They can be a bosonic state, they can be a fermionic state, but once you act on them with a supercharge, it annihilates the state. Or in other words, the state is invariant under that supercharge, and that's what we call a BPS state. And these states have very special properties. So that I'll try to explain that a bit in this slide. So I hope that helps a bit. So yeah, so we're tracing here over this Hilbert space of states, and what you see here is some fugacities that couple to charges. So some state with a given number of charges, say a state has charge 1 under all these, under J1, Q3, J2, etc. Then you just plug in the 1, you just plug in the charges for this state, and you get some product of P, Qs, and Fs here, and then the Dn will basically capture the number of those states. So that's what happens when you do this trace. Right, and so these J1, J2, and the Qs, they have some, yeah, they are the global charges of the states. And now there's this funny -1 to the f here inserted, which is very important. So this -1 to the f counts the f is the fermion number operator. So this operator gives a -1 to a fermionic state and a +1 to a bosonic state. And so what I was just telling you about these generic states that are related by a supercharge, they will have the exact same charges. So that's the exact same J and Q charges. So they have the same P, Q, and F structure here. But the bosonic one appears with a +1, and the fermionic one, because of this -1 to the F, appears with a -1. That means that their contribution will cancel. So generic states do not contribute to this so-called index. And only states that are annihilated, states that do not have a partner, these states will contribute here, because there's nothing to cancel their contribution. So that's what I mean here. So the -1 to the F ensures projection onto the BPS Hilbert space. So only getting contributions from states that are annihilated by Q, and that means that their Q dagger anti-commutator is equal to 0. And this you can express in terms of these charges. So these states will satisfy the condition that their energy is equal to the sum of these other charges. Okay, so that gives you some expression that basically counts the states with a fixed set of charges. And it's weighted by this minus sign, as I said. And now the crucial thing about these weighted degeneracies is that they are independent of deformations of the theory that preserve the supersymmetry. So in particular, the Hoofdcoupling, so the gauge coupling of the n equal to 4 theory, is such a deformation. So this means that I'm allowed to compute this superconformal index at weak coupling, in which it's a straightforward computation to do this trace, because we know we know the explicit Hilbert space, so we can just trace over that Hilbert space and get some expression here. But I can extrapolate these results to strong coupling. And that's what I wanted, because I want to analyze the gravitational interpretation, which is dual to the CFT only at strong coupling. Right? Yeah, and then finally, this is sort of the trace formulation of this partition function. But you can, in principle, you can also compute this by the path integral approach. And then the index corresponds to the path integral on an S3 cross S1 geometry. So the trace implies that you periodically identify time, that you perhaps know from the path integral. That's how you get to the path integral formulation of quantum mechanics. Okay. So yeah, sorry, I should maybe pause for questions about this. Okay. Now, there's a small puzzle in that these degeneracies, well, I should really say weighted degeneracies, at large n do not grow with n squared. So you might have thought that if there's somehow no cancellations in the degeneracies, and because we're then really counting 1/16 BPS states, then we should really reproduce the black hole entropy, because the 1/16 BPS states here, they should be the dual formulation of the black hole. So that's a puzzle that was noted a long time ago by Kinney, Madasena, Minwala, and Raju. But it's not really a contradiction, because there can be cancellations between states. It's not the absolute degeneracy of states, but it counts fermions and bosons with a relative minus sign. So there can be cancellations, and that is the reason that we don't see this order n squared growth. Okay, so that was the status for a very long time. But then there was a recent observation that by Hosseini, Christoph, and Zaffaroni, that there's this function. This looks like a very simple function. It's a function of the chemical potentials which are associated to the fugacities that were present in the trace, if you remember. So these are just the exponents of these fugacities. So this is a function of five chemical potentials that satisfy one constraint. And you can do a Legendre transform of this thing, and you get the black hole entropy on the nose. So you get that formula that I showed you here. So this was kind of a mysterious observation with no clear interpretation, but it was sort of suggestive. And so since then this field sort of resurrected in a way, and people started to try to understand where this function is coming from, right? And then a first paper at the end.
Sorry, Sam. Can I just interrupt? Can I just ask a question?
Yes, of course.
Are we talking about large black holes in ADS or small black holes in ADS?
No, these are large black holes. These are large.
Okay, so that's why 1/16 BPS.
Yes, exactly.
Okay, good.
Yeah. So they have an entropy of order n squared, and they have a macroscopic horizon. Yeah. Yeah. So then there was a very careful computation at the end of 2018 that showed that this black hole solution, this supersymmetric black hole solution, has an on-shell action. You can compute the on-shell action, but it's sort of a slightly tricky thing to do, but that was carefully done in this paper. And they showed that the on-shell action precisely reproduces this function. And then it's actually standard laws of black hole thermodynamics that say that you can get the entropy from the unshell action by a Legendre transform. So this is just so you could view this as a gravitational path integral understanding of where this function is coming from. But really, you know, we also want to know how it emerges from the CFT. So in the ADS CFT dictionary, the unshell action should be equal to some partition function of the CFT. And so it really is the aim became to also reproduce F directly from the CFT. And at the end of 2018, 3 groups were able to reproduce this also from the index. So that's a little bit surprising, and I'll comment on that just below, because Kinney et al. Seem to say that you couldn't reproduce it you couldn't reproduce the entropy from the index. So anyway, so these 3 independent works did this in various ways. In the same paper where they carefully computed this unshell action, they identified F on the field theory side as some Casimir-like energy, not too important what that means. A Korean group, including Choi and Seo Kim, they computed this by taking a certain limit of these chemical potentials tau and sigma, which correspond to P and Q of the index. And the reason that we call this a Cardy-like limit is just because this is a little bit similar to taking a high temperature limit. So that's why it's called a Cardy-like limit. And finally, Benini and Milan used an exact formula for the index called the beta ansatz formula, and they showed that in the large n limit, they also get F. Also a very careful computation. So how is this consistent with that earlier finding of Kinney and Maldacena et al.? Well, the crucial ingredient in all these papers is that the fugacities are allowed to be complex numbers. Whereas for the Kinney-Maldacena story, they treated these fugacities as real numbers. And that means that you can get a phase. You can, apart from just counting bosons with plus signs and fermions with minus signs, they can get phases, these contributions. And then you can imagine that, that you can obstruct these cancellations. And so that's the reason that this new work is still consistent with these older results. All right. Our approach starts from yeah, we're interested in further exploring this new development, and we start from the following. So it turns out that the index has somewhat peculiar modular properties under SL3Z. This was found in a very interesting paper by Abhijit Gade in 2020. And in fact, these modular properties allow us to compute the Cardy-like limit of the index. So I mentioned that here, that the Korean group was able to reproduce F from using a Cardy-like limit of the index. But they did that somewhat directly in the formula for the index. But this modular property can also be used to sort of, in some sense, more simply compute the Cardy-like limits. But this is very familiar from CFT2, where Cardy originally used SL2Z modularity of the CFT2 partition function to compute the high temperature limit. So this smells a lot like what happens in CFT2, although the details are different. And we know that in CFT2, modularity has a very natural gravitational interpretation, a very beautiful interpretation, and modularity is much more powerful also in CFT2 than just giving rise to the Cardy formula. So then it's natural to ask if somehow this peculiar modularity in 4 dimensions can give a similar is similarly more powerful? Can we exploit it more? And is there also a natural gravitational interpretation of that? So that is addressed in our most recent paper, and that's what this talk will be about. All right. So let me again stop for questions. All right. So I want to before getting to 40, so I'm keep on postponing the actual story. To just want to briefly remind you or explain you how SL2Z modularity in CFT2 gives rise to, has a very beautiful gravitational interpretation. So yeah, again, I'm sorry about the jargon. There's a lot of jargon here, so I hope you can bear along. So in two-dimensional CFT, you can also define a superconformal index, which also counts these BPS states that we were talking about. So and it's more common actually to refer to this object as the elliptic genus. Now, don't worry about this. This is just some canonical, so this K3 symmetric product of K3 is just a canonical example of a CFT2 that has a gravitational interpretation. And it's actually closely related to that D1, D5 system that I discussed in the introduction. Anyway, so the details are not that important. This is just some trace, and it only counts BPS states. And again, you can, in the path integral formalism, you can think of this trace as the path integral over the fields living on a two torus with some modular parameter tau. And here this modular parameter is related to the fugacity Q here, again by e to the 2 pi r. Now, the elliptic genus is something called the Jacobi form. This means that it transforms under this group, SL2Z cross Z2. So this, what it does is that this Z2, this just shifts the Z parameter, this shifts the Z parameter of the elliptic genus by periods of the torus. So the torus has two cycles, and we normalize one cycle to have just length 1. So we shift it by an arbitrary integer, and the other cycle then has length tau. And the fact that this object is a Jacobi form tells us that it has a very specific transformation property. So as you can see, it's almost doubly periodic up to this phase, right? So it has, and under SL2Z, so SL2Z, I hope you know, is the group of large transformations of the torus, where you sort of change the basis of cycles on your torus. And this SL2Z acts on the modular parameter tau by fractional linear transformations. And it also acts on the Z parameter like this. And again, because this is a CFT2 and this is Jacobi form, this object is almost invariant under these transformations, which is a very special type of invariance, which goes under the general name of modular forms, but yeah, specifically this is a Jacobi form. So it has this huge symmetry. All right. Well, these two properties imply that this object has some Fourier expansion in Q and Y. And moreover, it implies some symmetries between the Fourier coefficients, but it's not that important. So let me not dwell on that. What I want to say is that these symmetries are actually so powerful that you can define some truncation of this elliptic genus, where we're only going to take the part of the Fourier expansion such that this number is smaller than 0. That only depends on a finite set of Fourier coefficients. Okay, so that's some truncation of this full thing, and we call it the polar part. And now these symmetries are so powerful that actually the full function can be reconstructed just from the polar part. So it's a very, very highly constrained object. And this reconstruction lays at the heart of the gravitational interpretation. So this is called the fairy tale expansion. It was first discovered by, well, in the physical context, it was first used by Dijkgraaf, Madesena, Moore, and Verlinde, and later improved upon by Manschot and Moore. And it says that there's the actual way to reconstruct the elliptic genus from that finite truncation is by just taking the finite truncation and then summing it over essentially the modular group. So we're averaging this object over SL2Z. And that gives rise to the full function. Now there are some details here that I'm leaving out. That's why it's only an approximate sign here. But this is the essential gist of the fairy tale. And then you can work this out a little bit. And again, I put an approximate sign because there's some details into going from this side to this side, but it's not that important. But effectively then you can write it as this exponential times some corrections, which is still summed over this SO2Z. And this expression has a beautiful gravitational interpretation. So the idea here is that we can, on the gravitational side, so we were working with a CFT2, all these formulas are just CFT2 formulas. But now we know that this CFT2 has a dual description in terms of ADS-free, gravity in ADS-free. And the idea is that this sum can be interpreted as a sum over saddle points. So saddle points of the gravitational theory, which include just empty ADS-free, thermal ADS-free, and BTZ black holes. So that those are the saddle points of the Einstein-Hilbert action. And why? Well, you can ask, why do these saddle points live in some SL2Z family? Well, I try to illustrate that here in the figure. So you all know that you can think of ADS-free as sort of a cylinder. But because we're looking at the Euclidean signature, we have compactified time. So time has become a circle. So if you identify the two ends of the cylinder, you get a solid torus. So this is the solid torus, and the time that runs along the height of the cylinder is now this circle here, and the interior of the ADS space is. Well, that circle is the phi circle, and this phi circle, of course, contracts in the middle. So in the middle at radius 0, this circle, there's nothing left of this circle. But now we can do an S transformation that exchanges the A and B cycle of the torus. That's sort of the basic transformation in this group SL2Z, which, as I said also in the previous slide, this changes the cycles and exchanges, the S transformation exchanges the T cycle with the phi cycle. So now we get, again, a solid torus, but now the phi circle has become non-contractible, whereas the time circle is contractible. But if you think about it, this is exactly the geometry of a Euclidean black hole. So if you Euclidenize a black hole solution, you find that the time circle pinches off at the horizon, whereas, of course, the angular coordinate now is of finite size, because we only can go to the geometry pinches off at the would-be horizon, and there the phi circle is, of course, still finite and of size of the horizon area. Right. So this can be done for arbitrary SL2Z elements. So arbitrary linear combinations of you can exchange these cycles with arbitrary SL2Z elements. So that gives rise to all the saddle points. So this is then a sum over saddle points. And the summand can, in particular, contains the on-shell action of that solution. That's this part. And then it contains some other stuff, okay? That which you can think of as, you know, corrections to the on top of the saddle point. So we see that this pure CFT2 formula has a beautiful interpretation in terms of what you would expect for a Euclidean gravitational path integral. Okay, and I should also say that if you look at this thing and you consider a tau limit where you take tau to be a rational number, then this term blows up where for the term where C and D are equal to this, and that will be the dominant term. And then this is like then you essentially get the usual Cardy formula. And so you, in some sense, you could say that this fairy tale is like an exact version of the usual Cardy limit, or it makes manifest the Cardy limit. Let me put it like that. All right. Okay. Any questions about that? Okay. So then I can set up the more precise questions that we wanted to answer. So we can. So what we want to ask is whether this 4D modularity that I've been alluding to but haven't explained yet, does that give rise to a similar covariance property? So a similar modular property as we saw for in 2D of this Jacobi forms. Can we use that to compute more general Cardy limits of the index? So remember that we only computed the tau and sigma to 0 limit of the index, which give rise to that function f that we wanted to reproduce. But you can wonder, you know, from 2D we know that you can take more general Cardy limits, and that you can take the tau to any rational number, not necessarily 0, and you get these other saddles. So is there something similar like that for the index as well in 4D? And does this covariance imply an averaged expression of the 4D index? So we saw that modularity in 2D was crucial to obtain this fairy tale expansion, which you can think of as some averaging this polar part over the modular group. Is there an analog of that in 4 dimensions? And then finally, is there a natural gravitational interpretation for that? All right, so then we come to the real part of the talk, and let me check the time. Okay, yeah. So, well, I'm saying that this 4D index somehow has something to do with SL3Z, but unlike in 2D, where SL2Z can be understood as large transformations of the torus, it is not true that the geometry relevant, the background geometry relevant for the index, which is S3 cross S1, that certainly SL3Z does not have a natural action on this. So this SL3Z modularity has to come from something else, which I will now try to explain. So the relevant modular group will be a generalization of what we saw in 2D. So instead of SL2Z cross Z2, there will be an SL3Z cross Z3. And this acts on a free torus, not a 2 torus, but a free torus. So how it acts is that it shifts this Z parameter by periods of the torus, and SL3Z acts by matrix multiplication on the xi's. Okay, and now we can consider a class of 4 manifolds that are glued, that can be obtained by gluing solid free tori. So let me try to explain it. So here I've indicated a solid free torus. So a solid free torus has 2 non-contractible cycles, and it has 1 contractible cycle. So notice that the solid 2 torus that we saw before, that would just be this part. So this would be the cycle that contracted in the bulk, and this would be the non-contractible cycle. Now the solid free torus just has one additional cycle. Okay, and let's take two of these guys and then glue them along their boundary. Okay, we can glue them by acting with the identity element on these, so doing really nothing. So what you then get is you just identify this circle with this circle, this circle with this circle, and this circle with this circle. So that gives you just two circles, and then when you glue two of these disks, you get an S2. Okay, so here the manifold that is obtained by gluing with the identity element just gives you an S2 cross T2 geometry. Now we can do something a little bit more complicated. We can use an S transformation, SL3Z. The S transformation that exchanges the second circle with the third circle, and vice versa. Now it turns out that if you do this gluing, then the geometry is not anymore an S2 cross T2, but it becomes an S3, a free sphere with times an S1. That's precisely the geometry that we're interested in. So here we see how SL3Z still has something to do with this geometry, right? It doesn't represent the large symmetries of this geometry, but it somehow appears in this gluing construction. Okay, and this can be done in principle for an arbitrary element G in SL3Z, but we won't really make use of that. So that's not that important. Okay. Okay. Now it turns out that a specific supersymmetric path integral on such a manifold respects the splitting, meaning it respects the splitting in two solid tori. And this phenomenon is what is known as holomorphic block factorization. So what happens is that you compute the partition function on this manifold that is glued with some element G, and you get the following expression. So you get some sum over something that is factorized into two factors. And the interpretation of this, so the interpretation of these B's, which are called holomorphic blocks, is that they are these partition functions on solid free tori. So I sort of pictured this equality here. So the statement is that you're computing the MG partition function, and somehow we saw in the previous slide how this geometry splits into two solid free tori, and somehow the computation only cares. Somehow the computation factorizes into just the partition functions on these blocks, on these solid free tori. Okay. Okay, so yeah, I think that's the most important thing I want to say here. These the labels and vacua, and okay, this equality only holds up to a phase. So the intuition for why such a factorization occurs is because this path integral localizes on field configurations that are centered at the origins of these disks. So it turns out that the only non-trivial contributions to the path integral are localized here. So then, or on these two sides. So then you can imagine that that computation effectively factorizes, and that's very much due to the fact that this is a supersymmetric path integral. Okay, so now this idea of holomorphic blocks leads us to the modular property as found by Gade for 4D partition functions. So please bear with me. This looks more complicated than, but bear with me for a second. So we're interested in just a single term in this sum, and we now want to compute the partition function on a manifold that is obtained by gluing two solid free tori again, but using a product of these group elements. Okay, So that is just given by the two holomorphic blocks. And now I just multiply something in that is equal to 1. So you can see that these two guys just cancel these two guys. Okay. But if I now define a normalized partition function, which is defined as follows. So it's just this object, but we divide it by the partition function on the manifold obtained by gluing with the identity element. Then you can check that this equation reduces to this nice simple equation. So this tells us that this normalized partition function, which I indicate with a hat, on a manifold glued by taking a product of G1 and G2, can be written as the product of the partition functions on the manifold Mg1 times the manifold Mg2. Okay. So again, to picture this, here's the manifold that is obtained by gluing two solid free tori with G1 times G2. And now you imagine that you stretch this cylinder in the middle and you insert this resolution of the identity. And that essentially splits this manifold into two disjoint manifolds. That's the basic picture here. And this supersymmetric path integral has this specific property. Okay. So this is going to be the modular property that we're interested in. So it relates some partition function defined on G1 times G2 to this part. But for now, it looks rather different than the SL to Z or modular form property known in 2D. So what's going on? So this is perhaps a little bit highbrow, but I think it's important to say. But please. This slide is perhaps not that important, but I just want to say that it looks the modular property looks quite different, but it is in some sense a natural generalization. So to understand this, we have to think a little bit more abstractly about what the elliptic genus is. So the elliptic genus can be thought of as some element in a cohomology group in this zero of cohomology of the Jacobi group. So this is a group cohomology valued in meromorphic functions of the fugacities modulo phases. Now this sounds very abstract indeed, and I barely understand it myself, but so the concrete meaning of this is as follows. So if you know about cohomology, you know that cohomology is about closed forms, which means some differential form of for H0 a function that is annihilated by an appropriate differential operator. So in the context of group cohomology, that's very similar. So you can think of this H0 as representing G invariant functions. And the fact that there's a quotient here by M means that they have to be G invariant modulo phases, modulo M. Okay, so what does this mean? Well, there's this differential operator that maps you from H0 to H1, and it's defined as follows. So you take your elliptic genus, which is an element in the H0, and you act on it with the delta, and it computes for you. It gives you this difference. It's not quite a difference, of course. It's a ratio. And then the statement that chi is in H0, meaning that it's closed, means that it should be invariant, right, under this delta. But it's allowed to be invariant up to a phase, because we're considering it modulo phases. So that's sort of the concrete statement here. And then you recognize this as precisely the property of a Jacobi form. Indeed, so if we go back to our slide on Jacobi forms, we had the elliptic genus evaluated on some transformation SO2Z action on tau, gives us the original elliptic genus as a function of tau up to a phase. That's precisely what you expect for elements of this particular H0. Okay, so that's good. Okay, now that we have thought a little bit more abstractly about the elliptic genus, we can actually understand in what sense the property I showed you in the previous slide is a generalization of this modularity. It's in the following sense. So we can go to a higher, we can go one step higher in cohomology rank. So we can go from H1, and similarly as from H0 to H1, there's a map, there's the same map delta from H1 to H2, which now acts as follows. And this again, the statement that this X is an element in H1 is that it's invariant, that should be invariant or annihilated by this delta up to a phase again. Okay? But if you stare at this equation, you see it is of exactly the same form as the property we derived here using this holomorphic block property of these supersymmetric partition functions. So the conclusion is this set hat of G can be viewed as an element of the first group cohomology, where this group is now SL free Z cross Z free. So it's in that sense that it's a natural generalization. Okay, and this was sort of the main result of that Gade paper that I cited before. Okay, so this sounds rather abstract, perhaps maybe way too abstract. So let us now see. Let us reflect and see how this can be useful. So, well, let us first note that there are two difficulties that immediately arise with this new type of modular property that these 4D objects satisfy. Well, first of all, we've derived it for this Z hat, this normalized partition function. And this is a somewhat artificial construct. And we really want to, get information about ordinary partition functions, not these normalized guys. So it's not immediately clear how useful this is going to be. Similarly, okay, we can view this property as some covariance property, but it's kind of a weird covariance. It's not like in 2D. It's not a covariance under a large symmetry of the torus or of the background geometry, but it's rather something weirder. It's some covariance under the splitting of a manifold, like this. So that just sounds a bit funny, and you could expect that this might obstruct a natural ADS interpretation. Okay, but actually it turns out that these problems, okay, these are fair issues, but it turns out that these that studying the modular properties for this Z hat, which look kind of funny, is still very useful to ultimately study ordinary partition functions. Okay, so we have to bear with this somewhat abstract and not entirely clearly interpretable properties, but ultimately we can extract some real physics from this. Okay, so let us dive into this modular property in a little bit more detail. So one subtle difference is that the 4D modular property is labeled by a relation. So it's labeled by the fact that some element that is represented as a product of two can actually be factorized into G1 and G2. And instead, in 2D, a modular property is just labeled by an element in this Jacobi group, SO2Z. So that's a small difference. So if we want to find a useful modular property, we should not look for an interesting element in the modular group, but rather we should look at interesting relations in the group. And one type of relation that can be interesting is formed by finite order elements in the group. Finite order means that if you multiply the element enough times, you get back the identity. Okay, so, well, the normalized partition function of 1, because it's normalized, is just equal to 1. Okay, so this first equality is clear. But now, for this guy, we use that modular property that allows us to express the partition function on a product of two group elements as the product of the partition functions associated to the factors. And we use that consecutively. And then we get the following expression where there are n partition functions here. Okay, and so this tells us this somewhat quite non-trivial relation that somehow the product of all these partition functions with transformed arguments should somehow equal to 1 up to a phase. I should always say that we're working modulo M, where M is the space of phases. So that's true up to a phase. And you can now see why this is somehow useful, is that here, even though we do not compare two partition functions with different arguments as you have in 2D, but instead we have n of them, at least they are all defined on the same manifold. So that's sort of the reason why these finite order elements could be interesting. Now, it turns out that in the relevant modular group, G, which is SL3Z, finite order elements are only of order 1, 2, 3, 4, and 6. Yeah, for reasons that I don't have time to explain, we'll only consider order 3 elements. Okay, I just noticed that I'm already talking for an hour. Jeff, how much time do I still have? Then I can maybe skip some slides.
Shall we say 10 minutes? Is that okay?
Yeah, that should be fine. Yes. Yeah. Okay, so let me just discuss the simplest order 3 element in SL3Z. This is common. Well, we have denoted this by the letter Y, and this element permutes the 3 cycles of the T3 cyclically. Okay. So we can now evaluate the partition function on this relation, y cubed is equal to 1, because this is an order 3, clearly an order 3 element. And then you find this relation between the partition functions associated to this y element. So let me remind you that the subscript y here means that these are partition functions on the manifold that is obtained by gluing 2 solid 3 tori with the element y. And you can see we have a product of 3 of these guys with some different arguments. Okay, and they should be equal to 1 up to a phase. And this phase can be explicitly computed using that cohomological formalism. And it turns out that the phase is very closely related to the anomaly polynomial of the theory that is described by the partition function. So this was phrased as a conjecture. This equation was phrased as a conjecture by Gade. He proved it for SQED, and we also proved it for the n equal to 4 SUN theory. And it seems very likely that this should hold for arbitrary n equal to 1 SCFTs. You may compare this now to the usual modular property of that we know in 2D. Where, for example, the S transformation gives you this type of relation. So it looks a little bit similar, right? We have a partition function with untransformed arguments, and we have a partition functions where you have 1 over the arguments. And you might hope that this property can be used to compute the tau and sigma to 0 limit, which was this Cardy limit, which you can think of as a high temperature limit of this normalized partition function. But of course, more importantly, we really want to know if this helps us into computing the same limit for the superconformal index, because that limit should ultimately be related to the black hole, to the on-shell action of our black hole. Okay, so okay, so for that I have to take a small interlude, but the answer will be affirmative. So we even though this relation now only holds for this normalized partition function, it actually has a useful implication for the ordinary superconformal index. So for that, I have to briefly sketch the structure of the index. So as I mentioned in the introduction, the index was this trace over the Hilbert space, right? You can explicitly do that computation, and we did that in the paper of last year. And the structure of that computation has the following form. So it takes the form of a sum, and then you have some free factors here, where these labels, P stand for perturbative, because you can in some sense think of in a path integral computation of this partition function, this would correspond to the one loop determinants. So that's one factor. And then you have some non-perturbative contributions known as vortex and anti-vortex contributions. It's not, the details here are not that important. It's just important to notice that this has this general structure. And I just remind you here that this can be computed in the trace formulation, but also as a partition function on the S3 cross S1 manifold, which is the manifold obtained by gluing two solid free tori with this S transformation. Okay, and now it turns out that this property that we discussed on the previous slide actually has a direct implication for the perturbative part of the partition function. So the perturbative part of the ordinary physical superconformal index satisfies the exact same equation. And okay, the reason for that, you have to do a little bit of work, but the reason for that is roughly that this Y element is related somehow to the S2 free element. And it turns out that the vortex partition functions, when you plug in the normalized partition function, it turns out that the vortex partition functions cancel amongst themselves. So that's why you are left with this equation for the perturbative part. Okay, so I'll be a bit quick now in this slide. I will just say that that now we can use this modular property to compute this high temperature limit of the perturbative part by using the fact that for these guys that corresponds to a low temperature limit, essentially, similar to what happens in the usual Cardy limit in 2D CFT. So we can compute this limit in terms of a simple phase. So this is some polynomial that is known, okay, and simple polynomial that is known. And this turns out to we have an expression now for the perturbative part of the partition of the partition function of the index, but it turns out we don't have any. This doesn't tell us anything about the vortex parts, but it turns out that this is sufficient to compute the limit of the index at leading order, because the vortex partition functions only contribute at sub-leading order in this limit. And the end result is this object. Okay, and if you recognize this from the introduction, this was precisely that on-shell action for the supersymmetric AES5 black hole. So what we see is that we have used this rather abstract, somewhat hard to interpret modular property of a normalized partition function actually has a very concrete consequence for the superconformal index. Okay, and this is you could view this as as quite similar in spirit to what happens in 2D CFT, but as you've seen, the details are quite different, or rather different. Okay, and so this is a microscopic or CFT computation of the ADS5 black hole entropy. Okay, let's see. So I think I'm now almost out of time. So maybe I'll just skip through this. I'll just say that you can find more general relations that for the normalized index that allow you to get these more general arguments inside the modular property. And there's an associated phase that we computed, and it turns out that this allows you to compute these limits for arbitrary rational values of tau and sigma of the index, and this corresponds to on-shell actions of different type of gravitational solutions. So it turns, yeah. If you want, I can explain more about that later, but during questions. But let me keep it at that for now. And then my final real slide is that we now want to understand what these modular properties imply for the ordinary superconformal index. So we're going to reinterpret the modular property that had to do with these normalized partition functions in terms of what it implies for the index. And so we first use that fact that we can rewrite the modular property for the normalized partition function in terms of the perturbative part of the index. So we rewrite it in the following way. And now we imagine that we're going to plug this formula for ZP in terms of two other ZPs with transformed into arguments. We imagine that we plug it into the index. Okay, and then you can actually think of these guys as the holomorphic blocks. So this will be your BL and this will be your BR if you combine it with the appropriate vortex partition function. So indeed, define these holomorphic blocks as the product of this ZP and a ZV, and then we plug this in for the M is 0 and the general M case. So for M is 0, we get an expression like this, where the B's are defined here. And for general M, we get a non-trivial phase coming from here. And we get the same holomorphic blocks, but just with transformed arguments. Okay, and then this is our proposal for how you should think of the modular property in terms of a covariance for the ordinary superconformal index. So you can see that this is a type of covariance where there's some action on the some modular action on the parameters of these holomorphic blocks, and they should and what we know from these modular properties is that these expressions should be equal up to a phase. So this is the analog of that transformation property of Jacobi forms in the 4D index. So in words, the index is covariant under different ways of factorizing into holomorphic blocks. So there's a modular family of holomorphic blocks, and you can factorize in any one of them, and that gives sort of a covariance-like property. Okay, so then some open questions. Yeah, so there's the question of how to interpret these blocks on the gravitational side, these holomorphic blocks on the gravitational side. And there was some suggestion that you could define something called gravitational blocks. It should be the dual of the holomorphic blocks. Another question is whether the covariance implies an averaged expression. As we've seen in 2D, the modular property is crucial to get some averaged expression over the modular group. Similarly, is there some averaged expression here that would have a natural interpretation over as a gravitational path integral? And that's sort of suggested by the fact that these phases that appear in these modular properties are precisely the on-shell actions of solutions. So that's very similar to what happens in 2D, but we haven't been able to make this more precise yet. And then I'll just flash the main conclusions on the screen. And thank you for bearing with me. And I hope it was at least a little bit followable. I guess for students, it might have been a bit hard, but please feel free to ask any question, or if I want some clarification or whatever.
Thanks very much, Sam.
Okay.
Any questions? Nothing. Okay. So as I said, Sam is a postdoc at WITS, and I guess we're all kind of local these days. There's normally you would be visiting and you'd be around for the rest of the week. But if anybody has any questions, I recommend just dropping an email to Sam and ask him the question. I'm sure he'll be happy to answer. In any event, Sam, once things open up, how long more are you in WITS for?
I'll be here for another year, so
okay.
I'll be at least until October 2022. Okay,
so in principle, you can, you could well visit, except nobody's around at the university.
Let's see. I would love to visit, but maybe hopefully at the end of the year things return a little bit to normal. I'm not sure, but yeah.